In this video, we're going to start to look at how integration can help us define volume of some odd shapes. And the first technique we're going to use is volume by slicing. Now, there's two different ways that we can slice an object in order to find its volume. And the first way is going to be a general slicing method, or called the general or traditional slicing method. And that's where if we have a figure with a common cross-section. And so looking at this figure, this is an odd shape, but its cross-section is the same. It's this parabolic region that's outlined here. And that cross-section, if we slide this plate either up or down the volume anywhere from A to B, we see that the cross-section is always the same shape. It's always this parabolic shape. And so if we can write a function for that cross-section, we can then use integration to find its volume. Now, if we want to talk about, well, how do we find volume of an object? And let's look at if we have an area. So say the area is given by that A of X. So the area of this face here. If we just take a tiny little width here, take a little delta X, we multiply the area by that width, and that gives us the volume of that little section. Now, you might understand where we're going here with this in that, okay, well, if we do this an infinite number of times from A to B, and we make that delta X approach 0, so turn delta X into the differential dx, then we're left with this idea of an integral. And that if we integrate that area function, we are able to get the volume of the object. And so this diagram shows here's a delta x distance here, and make delta x a little smaller, and we have more of those cut up shapes, and make it even smaller, and we have even more, and approach to where n is infinity, and we're left with the full shape, the full volume, which we get through integration. So this gives us the general slicing method, and the formula for that is to integrate from A to B our cross-sectional area function. So the task here is finding what is that cross-sectional area function and then just integrating it. So let's look at an example. Let's say we have the curve y equals 1 minus x squared. And on that curve, we're going to use that curve and the area under that curve in the first quadrant. We're going to make that the base of our solid, and we're going to create these square pieces. And so we're going to have a square cross-section that we say is perpendicular to this x-axis here. So all these square pieces, so as we move closer to here, we have even smaller squares that rise up, and the squares get bigger and bigger as we get all the way over here to where the square is going to have a base of 1 and a height of 1. So if we look at all of these squares together, we see that this is the shape of the solid that we get from having a consistent cross-section of a square bound by this curve y equals 1 minus x squared. Now, as shown in the last slide, this dimension right here, this base, is the function 1 minus x squared. Well, how do we find the area of this cross-sectional area? Well, that area is the side length squared, and so the side length is 1 minus x squared, so this is just 1 minus x squared squared. Now, why is it the side length squared? What is this shape? It's a square. So to find the area of a square, we multiply the side by the length times width, which they're the same thing, so it's just the side length squared. So we can have our area function here, and we can use that to integrate. And we're going to integrate from 0 to 1 because that's our biggest x value, our biggest and smallest x value. We're going from x equals 0 to x equals 1. Well, this integral, pretty simple. We can plug in the 1 minus x squared, that quantity squared. We can square it, expand it, and then evaluate the integral. And the value of that integral is going to be 8/15 when we integrate and evaluate at 1 and 0. Now, we can do this with any type of cross-sectional shape. So let's say we have the two curves. We have the curve y equals x squared and y equals 2 minus x squared. And we're going to use the area between those curves as the base. Well, how do we find the area between those? We subtract we subtract the 2 minus x squared minus the x squared, so that becomes 2 minus 2x squared. That tells us the distance between these two curves at any given x value. All right, now what do those x values range from? Well, we know they range from -1 to 1. How do we know that? That's when they're equal to each other. Set x squared equal to 2 minus x squared. And so x is equal to plus or minus 1. Okay? And so if we want to create a shape such that it's bound by this base between these two curves, but we create semicircle slices. Instead of square slices that we had before, we have semicircle. Well, then if we have semicircle slices, in order to find the area of a semicircle, it's 1/2 pi times the radius squared. So that's our area function as a function of r, but we want the area function as a function of x, and so that's where this radius comes in. Well, what is our radius? Look at our diagram here. It's half of this distance between the curves. So we know the distance between the curves is this right here. Half of that is the 1 minus x squared. So we need 1/2 pi times the quantity 1 minus x squared squared, and that is our area function. Integrate that from -1 to 1, and we get the volume of that solid. So let's transition here to a different type of slicing, and it's going to come about because of a different type of solid. So let's say we have this curve, y equals some function of x. So we're given this function, and we're going to look at the area from A to B. And instead of taking a cross-section, using that as a base and taking a cross-section, we're going to revolve this around the x-axis. So we revolve this area around the x-axis. So picture yourself revolving this area around and imagine the solid it creates, the solid that it sweeps out as it goes all the way around. And so if we look at it stage by stage, as this rotates through one quadrant here, as this rotates through one quadrant here, we start to picture a little more and a little more of what this solid is. And so we get this conical type shape, but it's not bound by a linear edge, which we can find the volume of that using geometry. This is bound by a functional edge. And so it's bound by maybe a parabola, a square root, some function, but its outer edge, that curve, is bound by some function y equals f of x. And so the volume of this, we want to find this volume. We can still use integration to do this. And in doing it, let's examine what is the cross-section. If we look at this, because we revolved it, the cross-section of this is a circle. All right? In fact, it's a circular disc. And so that disc has a radius of f of x, and so we could find the area. Our area function here is simply just pi f of x squared. And so if we were to take this and find a volume by a tiny, tiny little width, and then add all those together, we would get the infinite amount of discs, which is the full volume, and we could integrate this function from A to B to find that volume. So this gives us a method that we call the disk method. Now, keep in mind, this is very important. This is for rotating about the x-axis. So if we're rotating about the x-axis and we're bound by some function f that is a function of x on the interval a to b, if we take that region and revolve it about the x-axis from a to b, then the resulting solid can be found by this integral, where we take pi times f of x squared, which, keep in mind, this is just an expansion of what we were just doing, in that we're integrating from a to b an area function, a cross-sectional area function. Because remember, what's our cross-sectional area? It's pi r squared. It's just the area of a circle. And that's all we're doing. And our radius is our function. So the pi function squared, just remember area of a circle, and that's what gives us this disk method. So let's look at an example where we have the function x plus 1, that quantity x plus 1 is being squared, and we want to take the solid from 0 to 2 and we're going to revolve it about the x-axis here, okay? And that shape that we get from revolving it. And so we get this horn-type shape. It has a parabolic curve here, and so it's almost like a funnel. We want to know, what's the volume of that? Well, let's look at its cross-sectional area. Well, its cross-sectional area we know is a circle, pi r squared. So it's pi times, well, what's our radius? Our radius is our function. It's f of x, and we need to square that. So that leads us to a radius of pi times the quantity of x plus 1 squared. Okay? We integrate that from 0 to 2, and then we're home free. And we get the actual volume. Okay, so we see that we're going from 0 to 2, and we expand this a little bit, and we get a volume of 242 pi over 5. A slight expansion to the disk method looks at a situation where, well, what if we have some function f, but we also have another function g, such that we want the area between these two to be revolved around the x-axis. So we're losing some of this area slash volume down there. So we're going to have a hole in our object that is being revolved. So if we look on the right here, it produces this object with a hole in the center. Now, we want to find the volume. Now, there's two ways we could do this. We could find the volume of just revolving the f around, and that would be the whole solid. And then we could find the volume of that hole and subtract the two. Or we can put these together looking at, well, what is that shape? That shape is a cross-sectional washer, is what we call it, in that it's a circle within a circle, and there's a hole missing. And so how do we find the cross-sectional area of that washer? Well, that's pi times the outer radius squared times the inner radius squared. All right, or excuse me, not times, subtracted by the inner radius squared. So we want to take pi times the difference of the square of the two radii, finding the cross-sectional area of that washer. So this is called the washer method, and it allows us to find the volume when we have two different functions that when we revolve it is going to give us a little bit of a hole. And so it's the same thing as just finding the two different volumes separately and subtracting them, but we can put it together in one integral if we choose. So for instance, say we have y equals x squared and y equals radical x. These two join at the point 1, 1. Once again, how do we find that? Well, we set those two equal to each other, do some algebra, and solve. The area between them creates this shape, and if we want to revolve that around the x-axis, we get this volume pictured here. Well, how do we do that? Well, we want to apply our formula. We need pi times f of x squared minus g of x squared. Well, f of x squared is x, g of x squared is x to the fourth. So we subtract those, multiply by pi, integrate from 0 to 1 because we're starting at 0, going to 1. We can also revolve these around the y-axis as opposed to the x-axis. And if we do that, it's essentially the same thing, but we have to have everything in terms of y. X needs to be a function of y in both of these cases. We don't want to write them as a function of x. And our radii are our distance from the y-axis. So the leftmost one is our inner radius, and the rightmost one is our outer radius, if we're graphed in the first quadrant. Obviously, if we're graphed in the second quadrant, then that is reversed. So this gives us our translations if we are to revolve about the y-axis in both the washer method and the disk method. So these are the two methods that we'll use for revolving areas around an axis. And if we have a consistent cross-sectional area and a base that we have based on a function, then we'll use our general slicing method. Both of these use slices of consistent cross-sectional area.